By the way, you might have noticed that your names are there. Yeah? And basically, the reason why all of your names are there is because this is how I graded your exam. So if I click on any of those names, you'll see your file that I used for grading. And then after I graded for all of you, I just printed the let's say the graded exam as PDF file and sent it to you. This is why you see your names there. So don't think that I have a file on each one of you. You know, sometimes some governments have files on citizens. Okay, and whatever you do, they just put whatever information they have on you in that file. So this is not what this is not why you have your names there in OneNote. It's just because this is how I graded the exam for each one of you. Right. So what I was saying, gentlemen, is inshallah, by tomorrow, I'm almost sure that we'll finish the material. Maybe if there's anything remaining or so, it's just going to be something minor on Saturday. Right? So in fact, most likely I'll give you some. I'm sorry, on Sunday, Monday. I think I'm not sure. There are supposed to be classes on Monday, so because someone told me yesterday, and I'm not sure whether it was from your class or the other class, that there's no class on Monday. Theoretically, there are classes on Monday, right? Or am I mistaken?
I think so.
Yeah. To the best of my knowledge, there are classes on Monday. But anyway, even if there are classes on Monday, I will probably cancel that class that you go study. I'm going to be available, but I'm not going to give you a lecture. This is basically what I'm saying. Okay. So if you have any questions or so, I'll be available. You can just connect with me, and I can answer your questions. Okay. So what we've been talking about over the past 3-4 classes, gentlemen, since we came after the vacation, we have been talking about discrete time signals. And let me just remind you very quickly, at the beginning, we talked about discrete time signals that are represented using continuous time signals. Now, this may seem to be a contradiction. No, it's not a contradiction. What I mean is, we said that nature, life, most life is continuous time. The signals that your ear hear is continuous time. Your voice is continuous time. For example, your weight, how heavy you are, if you plot it versus time, it's continuous. I can measure how much you weigh at every time instant. I mean, if you go to the scale, it doesn't say, well, if you go to the scale to find your weight, it doesn't tell you, well, you have just taken your weight an hour ago. Between last hour and now, your weight is not defined or doesn't exist. At any time, I can always find your weight. And if I plot it versus time, it's going to be a continuous signal. It's going to be a signal that looks like this. Yeah. Now, it may change, it may not change. This is another issue. But it will be continuous time. Whenever we talk about discrete time signals, we can also represent discrete time signals, but if they are continuous time. How do we represent them? Using impulses. And this is basically what we talked about at the beginning. When we started talking about discrete time signals, we said that I will represent discrete time signals, but as if they are continuous time signals. By taking a signal and multiplying it by a train of impulses, a sequence of impulses, long sequence of impulses. The impulses will cancel everywhere except, it will cancel everything of the signal except at the locations of those impulses, where each impulse now will contain the information about the value of the original signal. Right. And then we said, now forget it. Now we are not interested in using continuous time signals to represent discrete time signals. Now we're going to be talking purely about discrete time signals and systems. And last class, I talked about the difference between them. This is how continuous time signal will look like, either this or that. But this is how discrete time signals look like. And if you notice in here, there's nothing there. There's nothing here. We don't have a blue line there that indicates that it is 0. Okay? This is a very important point, gentlemen, that discrete time signals for times between samples, they are not defined. They're not equal to 0. They are not defined. Okay? You do not say that they are equal to 0. They are not defined at all. So this signal is only defined at -5, -4, -3, and only at integer values of the time variable, which is n. We don't use t, we use n. Now, I remember after the class yesterday, I remember that one of you asked me, which is, I think whoever asked me, I think the class before it. I'm not sure, but I think so. Today is Wednesday. I think probably on Monday or so. One of you asked me, like, if we sample a signal every half a second, how do we represent it in as a discrete time signal? Yeah? Do we represent it as a discrete time signal like this? This is, let's say, 1, 2, 3, minus 1, minus 2, and minus 3. If we sample a signal at, let's say, with a sampling rate which is equal to 2 samples per second, or basically Ts is equal to 1 over 2, meaning every 1/2 a second we take a sample. Do we represent it this way? And the answer is no, you do not represent it this way. Even if you sample a signal, gentlemen, at a sampling rate which is equal to 1/2 or 1/4, not sample rate, I'm sorry, a sampling period that's equal to 1/2 or 1/4, meaning the sampling frequency is 2 or 3 or 4 or 5 or 7 hertz, something like this. Meaning every second we're sampling at, we're taking more than one sample. Notice that the n in here, okay, the n that we have in there, the units of this n is not seconds. The units of this is samples. So if you sample at Ts equal to 1/2, meaning sampling frequency that is equal to 2, still this is what will happen. Yeah? So you're going to put the samples only at integer values of n. Now you may say, this looks like a contradiction. No, it's not. Think of it this way. Once I know what is Ts is equal to 1 over 2. Meaning, if I'm interested in converting this into, if I'm interested in plotting it where this is in seconds, yeah, then I know that the 1 will come to 1/2. The 2 will come to 1. The 3 will come to 1.5, and so on. So this now, if I have the t there in seconds, yes, this will come in here. This is 1 over 2, 2, I'm sorry, 1. This is 1.5 or 3 over 2, 2, and so on. Okay. So each sample now will go to the corresponding value of time that it represents. But this is only if you represent the signal, if you represent the x-axis as seconds. Whenever we use the x-axis as n does not have the unit of seconds. N has the unit of samples. So basically what it says is that this is the 0th sample. This is the first sample, second sample, third sample, fourth sample. I will not be able to, if you ask me, okay, plot it versus time in seconds, I'm going to tell you, before I do this, you have to tell me what was the sampling frequency or sampling period that you used. If it was equal to 1, yes, then this will become equal to 1 second, 2 seconds, 3 seconds, 4 seconds, and so on. If it was equal, if the sampling period was equal, for example, to 1 over 2, then this becomes equal to 1 over 2 seconds. This becomes equal to 1, 1.5, 2, and so on. Okay? So always, this n represents samples. It does not represent seconds. Okay, gentlemen? I hope that this concept is clear. And then we talked about how do you relate between continuous time, and I added yesterday, I spent maybe 2 hours, 3 hours, probably even more, okay, on adding some of the figures and adding some material, okay. So I added, sorry, this is cut again, it needs to be fixed, okay. But basically, this is how the impulse looks like in time domain, and this is how the impulse looks like in not time domain. I'm sorry, in continuous time. This is continuous time in here. Red is continuous time. Blue is discrete time. And I intentionally did this so that, there's nothing that says in books that continuous time is always sketched in red. In fact, books usually don't have colors. But I like, since I can use colors in here, I like to use colors there to distinguish between things. Okay. So I will try as much as possible whenever I need to sketch in the bottom. I will always sketch continuous time in blue, while continuous time in red and discrete time in blue. Okay? But this is basically the impulse in continuous time, and this is the impulse in discrete time. And notice that there's nothing in there between the different samples. Okay? This is the step in continuous time, and this is the step in discrete time. This is the ramp in continuous time, and this is the ramp in discrete time, and so on. Okay? So we talked about those last class, and then we came to transformation of discrete time signals. And I remember I talked about this. We said that always, when you can always flip, there is no problem. But when you do time shifting, the amount of time shift is always an integer. You would never replace n0 there or put a value for n0 there that is equal to 1.3 or 9.3. Okay, and always the n0 there, the time shift that you do to the right or to the left, has always to be an integer. And then we talked about this, and I haven't finished this material. Okay, so this is why this is still red. Okay, but inshallah I'll fix it before I upload the lecture. Probably I'll upload it during the weekend. So we talked about time scaling, and we said that I can scale either. I can have a equal to something like 1/2, or I can have a equal to 2. If a is equal to 1/2, this means expansion. Now, when you expand, you have always to fill in the locations which were vacated by the samples. Meaning, let me just remind you of this. I will add some figures that will show you this. This is why I didn't add it, because I knew that it will take me some time to add. Okay, to create those figures. When you expand, gentlemen, a signal 1, 2, 3, 4, 5, 6. Okay, the one, for example, if I expand it by a factor of 2, meaning a is equal to 1/2, so I'm trying to sketch x of n/2. The 1 will go to 2. 4, 6, 5, 3, and 1. Okay, the 1 will go to 2. The 2 will go to 4. The 3 will go to 6. You always expand, by the way, by integer factors. Expand by integer factors or shrink by integer factors. Okay? So this is what will happen. Now, what happens to those locations which do not have anything? We don't have anything in here at 1/2 that will go to 1. So what do? We fill them with zeros. It doesn't mean that the original signal in here had zeros, gentlemen. Please pay attention to this. Because I put in here a 0, it doesn't mean that the original signal there had a 0. No, it did not have anything. But whenever I have a sample there, empty sample, in which I need to fill it with something, and nothing from the original signal fills it, I fill it with 0. So the signal in here will look like this. Generally, if you expand the signal by a factor of 2, this is how it will look like. And if you continue further, every other sample has a value, okay? And every other sample has 0. Let's say 0 some value, 0 some value, 0 some value, and so on. So on the right and on the left. Okay. I also have similar points on the left-hand side. This is for an expansion by a factor of 2. If I had an expansion of 3, by a factor of 3, I'll have 2 zeros filled by a sample, and then another 2 zeros filled by a sample, 2 zeros filled by another sample, and so on. If you do the opposite, if you shrink, if you compress in time, what will happen is now you'll have to cancel some of the samples from the original signal. Some of the samples from the original signal will not be represented in the compressed signal. Okay, so some of the samples in the compressed, some of the samples in the original signal will not go anywhere. You simply cancel them; they just disappear. So, in fact, a question just came to my mind, and honestly, it's a very good, I think, exam question. But since it came to my mind and I mentioned it, I'll explain it to you. Okay? But honestly, yeah, if it came to me after the class, I would have probably put it in the exam. Okay? Let's say I put for you something like this: a signal that contains 4 samples: 0, 1, 2, 3. Okay? Let's say this is 1, this is 2, this is at 3, okay? And at 4, let's say it's equal to 3. Okay? I took this thing and put it into a device that does this. Yeah, basically this is x of t and an input, and I'm finding y of t, which not x of t. My apologies, x of n. Sorry. Okay? And I'm finding, because I'm used to t, so this is y. Okay, y of n, which happens to be equal to x of n divided by 2. Okay, and then I put it into another device. Let's say this is now y, so z of n is equal to y of 2n. Okay? If I have this device and I take the same signal now and put it into another, let's say, 2 blocks. Okay? Where this block in here goes there and this block comes there. Okay? And let me call this W in here, W of n, and K, and W X, Y, Z, F, for example, F of n. Okay? Will F of n and Z of n be the same? Do you think that they're going to be the same or not? You see, what I'm doing in here, by the way, I'm compressing by a factor of 2 and then expanding by a factor of 2. Okay, this is the lower one. And the upper one, I'm expanding by a factor of 2 and then compressing by a factor of 2. Will they be the same? Clearly, if you do the figures and so on, you'll probably be able to figure it out. But logically, anybody has any answer?
I think not.
Why not? You're absolutely right, but why not?
Some of the points will be missing if we did it the reverse way or something.
You're absolutely right. Yes, you're absolutely right. Okay, what your answer is perfectly right. You see, when you expand, you don't lose any points. What happens to the when you expand, you'll get points that are vacant, not filled with anything. What do? You fill them with zeros. Right? We said this is what happens when you expand. Right? Then when you compress, what do you think will happen? Those points that you filled with zeros are going to disappear. So you return back to the original thing. In fact, this and this will be exactly the same as this. However, when you compress first, some of the samples will be lost. Now, when you expand, what happens to them? They get filled with zeros. So clearly, this is not equal to that. And clearly, if this one is equal to this, but the second one is not equal to that. So clearly, those are not equal to each other. Okay, but they might be equal to each other only if you have special signal. For example, if it happened that I had a 0 in here and a 0 in there, yes, then by compressing, those samples will get cancelled. Okay, and then when I expand, I fill them with zeros, which results in the same signal. So in this situation, yeah, I'll get the same. But this is clearly a special case. In general, if I have signal that does not have zeros, then when you compress, you lose some of the data. And this is the problem with compressing a signal in time, meaning, I think I called it last time, or I told you, it's called decimation. You are basically every second sample, for example, you're throwing it away. You lose information. When you expand the signal after that, you don't get exactly the same information. You get the compressed, let's say the information after losing some of the data, you just get the same information, but it's a little bit expanded. Yani the information does not come back. This is basically what I'm saying. Okay. Right. So I think this is the thing that I wanted to mention about time scaling. Where did I go? Put this down. This is the thing that I wanted to mention about time scaling. Okay. So inshallah, I'll fill all of this information. I'm sorry, I'll put it in there. Okay. And then we talked about time shifting. We said that time shifting is always by a factor of an integer factor. Time shifting does not lose information. It does not give you any additional information. It's just the same signal shifted to the right or shifted to the left. Okay. So it doesn't cause any loss of information or any gaining of information or anything like this. Okay. Now, amplitude transformations are exactly the same as what we have learned in for continuous time. I'm not going to go over them, but even this, I haven't fixed this, by the way. All of this needs to be rewritten. Okay, but you see that I'm almost, what I'm going to do is I'll just change the parentheses there to square brackets and change the T to N, because the same thing applies whether we're talking about continuous time or discrete time. Okay? For amplitude, no change at all. But so now we're done with this. Now let's talk about discrete time systems. We have talked about this.
So the only problem is with the time scaling, right?
With the time scaling, yes, yes. You're absolutely right, yes. The only thing that you need to pay attention to is time scaling. It's the one that is, requires a little bit of thought. Because it's, in the continuous time, if you have, think of it this way, if you have a picture on your computer and you stretch it, yeah, if the resolution is very high and you stretch it, you get exactly the same signal, صح? Or exactly the same picture, but it's stretched, for example, in width or in height. But if you have not a picture, you have points that are scattered, and you stretch them. Okay? Now, in places where the original samples existed, you have to fill them up with something else. Okay? And this is basically why the time scaling is different between continuous time and discrete time. Well, otherwise, the amplitude, it's exactly the same. Okay, so now let's talk about discrete time systems. Okay, so far we have been talking about continuous time. We have talked about signals. Now we're going to be talking about systems. Believe it or not, all of this material, or most of this material, in fact, I deleted a lot of it. Okay, this material was just copied from above. I just went and changed these parentheses to square brackets because it's exactly the same. No change at all. I mean, if you have a discrete, and I added in here dt and dt. If you look at this picture in your notes, you see it's exactly the same, except that this was x of t, and this was y of t, and this was just saying system there. Right? And in here we had delta of t, and we had h of t. Okay? So those are exactly the same principles, exactly like what we had with discrete time, with continuous time, exist in here. In fact, even I'm mentioning that the output in here will be equal to the convolution. And yesterday I was looking at your book, and I'll say that maybe, I don't know, 100, not 100, maybe 60, 50 pages of the book, I would consider it to be repeated. Why? Whoever wrote the book, or those 3 or 4 people who wrote the book, could have said that the same thing that happens with continuous time happens with discrete time. And clearly, the operations that you'll have to do are slightly different, because in here we have summations, over there we have integrations, but the principles are exactly the same. The book has derived, let's say, the convolution. Yeah? It has also talked about those transformations in details. Okay? And I kind of skipped most of them because most of them are exactly the same. The book also talks about the properties of systems, of discrete time systems, and then also the properties of this special case when you have linear time invariant systems. Just like it did with the continuous time. I'm not going to talk about all of those because they are almost all the same. And in fact, I don't want you to even bother about them. I will probably not ask you about the properties of systems. All I care about in here, in this topic, or in this chapter, is how do you deal with signals that are input into a system, and how do you get the outputs, basically, okay? And how, more or less, how do you deal with how do you work with the signals, discrete time signals that are input into discrete time systems? Don't worry about the properties of systems, of either discrete time systems or linear time invariant discrete time systems. Don't worry about those. I'll never ask you about them in the final exam. Okay? And anyway, they are more or less similar to what we had before. Okay? So I'm not going to talk about this. In fact, I will apply this on an example. If I have time today, I'll apply it on an example just to show you that this is in general much simpler, not always, but sometimes much simpler than dealing with continuous time. In continuous time, you have to integrate. In here, all you have to do is just add. And you'll see in the example that I'll give you, I will add only, add numbers. Okay? Now, we're talking about discrete time systems. I think I have, I think one of those topics is supposed to be, oh, okay, no, I'm fine. Right? This material also was obtained from the beginning of the semester. If you remember, also, if you go to this material, you see that I just copied it. It was in there. It was saying continuous time. I just changed it to discrete time. And I don't remember that if I changed all of this or not, but I'll change it, inshallah. I think I changed most of it, right? But maybe not everything. You see, this is exactly the same material. Whenever you talk about discrete time systems, you will have one of several blocks. One of the blocks is called the transformation block, where the transformation block could be either multiplying by a number, adding a number, multiplication by a time function, meaning that this thing, whatever you put x of t in here, the output there will be some function f of n multiplied by x of n, meaning every sample of x will be multiplied by a different value that depends on the corresponding sample of n, of f, I'm sorry. Right? The difference between this And the first one is every sample of x is multiplied by that same constant, 3, for example. So the whole signal gets scaled up or scaled down by 3 or minus 3 or something like this. This one, no. Each sample of x gets multiplied by the corresponding sample of f. Okay? Or you could square every sample of x or raise it to the power of 3. Or you could take e to the power of different samples of x. Or you could take the natural log or cosine or time shift, for example. You could do time shift. Or this is basically, if you remember, this is what we talked about last time. This represents the derivative in discrete time systems. This represents the derivative, okay? And this represents, by the way, the integration, more or less. And maybe I'm calling it derivation, but they usually don't call it the derivation or so. But this represents the derivative, and this represents something like the integration. Okay? And anyway, and all of the possible blocks that exist in continuous time also exist in discrete time. Or you could have a block that takes 2 inputs where it adds the 2 inputs to produce. Sorry, I didn't fix this, so this should be. And my apologies for this. I worked on the lecture late last night, for maybe 3 or 4 hours, but I didn't have time to go over it, let's say line by line, to make sure that everything is okay. The same thing here. I could multiply 2 signals. Okay. Now, one of the things that are often slightly different in continuous time, and I intentionally put it there, is a delay block. In continuous time, gentlemen, I'm sorry, in discrete time, you have a block that will delay by 1 sample, which is usually called D. You see a block, and there's a D on it. The D basically there stands for delay. It's a delay by 1 sample. Now, you could have something similar to it in continuous time, but in continuous time, there's not much meaning for a delay by 1 second. Or a delay by 5 seconds, for example, or a delay by 2 seconds, okay? I mean, 1 second delay, or 3 seconds delay, or 2.2 seconds are all delays. In discrete time, the situation is a little bit different. A delay by 1 sample means the sample that is in here will go to the next location. The sample that is here will go to the next location. The sample that is here will go to the next location. I cannot have a delay of 1/4 of a second, or a delay of 2.2. The minimum delay I can have is 1 second. And that's why usually in systems, discrete time systems, you see some blocks there that have D on them. It's okay. Let me just tell you something. It's either D or it's going to be Z minus 1. You'll understand why it's Z minus 1 later. Okay? Probably either later this class or next class. If you see D or Z minus 1, they mean exactly the same. D means a delay by 1 unit. Z minus 1 also means a delay by 1 unit. You'll understand it, I promise you, inshallah. If not this class, next class. Okay? So this is basically a delay by 1 unit. Notice, by the way, that I wrote in here a delay. If you look in here, this is the delay. So I could have used a transformation block in which the input gets delayed by n0, which is equal to 1. Yes, but there's a special, let's say, place for that delay by 1 unit, by 1 sample. This is why very typically they don't. Yeah, I don't know. Some people will probably call it a transformation, but very often you'll see in many systems, many discrete time systems, that delay by one sample is always preserved, and it is, let's say, represented by as a special block. Okay, gentlemen. And what I'm trying to say, gentlemen, is it's not different from this one. The lower one, in fact, is kind of a special case of this. It's just that because it happens a lot, they dedicate always a block that is called a delay by 1 sample. Not 1 second, but by 1 sample. So this is kind of the 3rd or 4th block. Now, I'm not going to go over those. I'm asking you here, can you tell me what is y of t? Well, I'm sorry, y of n. What did I do? I just put one. I think I wanted to put another example. Just put one, okay? What I'm asking you there is to find. Sorry. The computer is a little slow, so it's. Okay. So I'm asking you to find y of n in terms of x of n. Okay? This is a trivial example almost. where x of n in here gets squared, and in here it gets delayed by 1 second, and then you add them. Okay, so this is quite simple, but clearly this could be more complicated than this, similar, for example, to the one that I gave you in the exam or the one that I gave you in the quiz and so on. So it could be slightly more complicated, and it might be even more complicated if it has what we call feedback loops. If part of the output in here goes and gets fed or added to the input, for example, yeah, then analyzing those systems becomes more complicated. But it's not more complicated than the situation of the continuous time. It's exactly the same as continuous time. Okay, more or less, almost the same complexity as continuous time. Okay, yeah, this was the second example that I wanted. Okay? I'm asking you there, okay, to show the block diagram of the differentiator and to show the block diagram of the integrator. Now, the differentiator is quite simple. In fact, let me do them very quickly for you. The differentiator, what do? I feed x of t directly to the output, so this is y of t. No, sorry, I keep saying x of t. I mean x of n and y of n. Yeah, but I need to take x of n, delay it by 1 second, or put a d, and then subtract it here. So I have to put an adder. Now, whenever you have an adder, by the way, I think I forgot to mention this when I talked about the adder block. Sometimes when you're talking about an adder block, gentlemen, inside the adder block you'll always have a plus. So you know that you're adding, but sometimes before the different inputs that you have that are coming to that adder block, you see signs like this, plus and minus. This basically means you take this as it is, yeah, and you take the second one here with a negative sign. This is one way of doing it. Or if you didn't understand this, if you didn't know this, you could have also done it this way. What can I do? Just put a minus, whatever. So, minus something like this. Okay? And the meaning of this is multiplied by -1. And then feed it there. So this is basically the block diagram of what we call the differentiator. It's not really a differentiator, but it acts like a differentiator in the discrete time systems. Okay? The integrator is slightly more complicated because the integrator always adds the input to an accumulated amount. Think about it. What does the integrator do? I have 10 so far that resulted from adding all of the previous samples. Okay, I'll add to it the current sample. Now it becomes 13. I'll add the next sample to the 13. It becomes 17. I'll add the next sample, which is -2, to the 17, which becomes 15, and so on. So every time you keep adding whatever amount you already have to the new sample. So this is basically how, yeah, if you think about it, this is how it will look like. I'm just going to do it very quickly for you. And here I need to add or put an adder. Let me see. What I need to do is, so this is basically the integrator. X of n at infinity, or at, I'm sorry, at minus infinity, assume that I have in there, let's say this is y of n. I'll show you that. Let me just make sure. Yes, this will work. Okay. What happens is put x of minus infinity. Okay. This was the first sample that I had from x of t. Okay. So it comes in there, and y of n becomes equal to x of minus infinity. Right. So in there I have x of minus infinity at that time instant. At t equal to minus infinity, or not at t equal to minus infinity, but when n is equal to minus infinity, okay, the output basically is equal to the input sample. Now what happens to this? This value gets delayed by 1 second, and it gets added to x of, let me not take minus infinity, let me take x of minus 1000. Assume that infinity is equal to minus 1000. So I'm starting with x of minus 1000. Okay? So in here I have x of minus 1000 now. Okay? Which means that the output at n equal to minus 1000 is equal to this. Now, when the next sample comes, which means that n is equal to minus 999, okay? What happens? This was the answer at minus 1000. It gets delayed by 1 second, so it will appear at the output in here of this delay at at n equal to minus 999. So it gets added to x of minus 999. So the previous result that I had, which was this, gets added to this. And now the output becomes equal to the sum of both of those, because both of those are added to each other. Okay? And this becomes basically the answer in here. If you think about it, at n equal to minus 199, I'll have x of minus 999 plus x of minus 1000. Now the whole number here gets delayed by 1 second and appears at minus 998. And it gets added to the value of x of n at minus 998. So you see, I am accumulating at this point all of the previous samples. And this is basically nothing but the integration. Y of n there basically becomes equal to the sum of all of the samples of x of n. This is how you combine all of them. You see, for integrations, always I need a feedback loop. For differentiations, I don't need a feedback loop. Okay? But so I just wanted to mention this for your information. Now, okay, let me just talk about this concept now, because we will use it inshallah next class, in the last class. Now we know that some continuous time systems, sometimes they were represented using their differential equation. If I have a circuit that contains some capacitors, inductors, and resistors, and so on, and an input, and I'm asked to find the output, generally I'll see that the output, y of t, will be represented in terms of x of t, or some versions of it, x of t minus 1, or whatever, or they will be related by a differential equation that looks like this. Maybe sometimes higher degree, lower degree, that's another issue. But the input and output are related by a differential equation. Now, do we have something similar to this in discrete time? And the answer is yes. In fact, we talked about in the table last class that we have something that resembles the second derivative. And this is basically it. I just copied it from above. Okay? I copied it from above, but I delayed it by 1 second. Okay? Just because I didn't want y of n plus 1. Okay? So I just delayed it. Anyway, yeah, this is just something technical. Don't worry about it. Okay? But this is something like the second derivative. Subtracted from it 2 multiplied by the first derivative of y. And this is the first derivative of y. It's a delayed version of the first derivative. Okay? Added to it 3 multiplied by y. Okay? And maybe I should have changed this to 2. Okay? Equal to x of n minus 1 or minus 2. N minus 2, let's say. Okay? So this basically, what I'm trying to say, gentlemen, here is this is kind of the discrete time version of this. This is continuous time. The upper one is continuous time. The lower, the orange one, is simply kind of the discrete time form of the continuous time differential equation. Okay? Very often, when they're talking about the discrete time equation, they write it such that it is y of n on one side. Wherever you see y of n, I think there was another y of n. I'm not sure. Yeah, this is also 3y of n. I combined both of those together into y of n and moved everything else to the other side. All x's, everything else, and all previous values of y, I move them to the other end. So you end up with an equation that looks like this. Maybe I need to check them. Honestly, I wrote this very quickly last night, so I'm not sure if it's accurate. But basically, if you see an equation that looks like this, y of n is equal to something in terms of previous values of y of n minus 1 and y of n minus 2, and maybe I need to add this to this. Okay. In addition to versions of x, or x of n minus 1, or x of n minus 2, and so on, we call this the difference equation. It's always called the difference equation. So we'll work on it inshallah next class, but understand that this is called the difference equation, which is equivalent to the differential equation in continuous time. Okay. Now, properties of discrete time, linear time invariant systems. If you noticed in here, I did not even write them, and maybe I'll add them, maybe not, but they are exactly the same properties. And you already know what will make a system be, let's say, memoryless or not. If I give you h of n equal to, for example, 3 delta of n minus 2. Okay? Since the impulse response is not an impulse at t equal to 0, only if the impulse response had component at 0 only, then it will be memoryless. But if it has any component that is to the left of 0 or to the right of 0, this means that it has memory. Okay? Linearity. Same principle exactly. If I have a system like this, put an input which is x of t and x1 of t and see the output. Put an input which is x2 of t and see the output. Put now a combination of x1 of t and x2 of t. Let's say a x1 of t plus b x2 of t. And see, is the output now in this situation equal to the sum of the two? If it is, it's linear. If it's not linear. Invertible. If every input produces only a single output. Okay. Causality. If the impulse response only has, let's say, non-zero values that are at 0 or to the right, it becomes causal. If it has any component that's to the left, for example, if h of n is equal to 3, delta of n, sorry, delta of plus, square brackets, n plus 2. Clearly, if you sketch this is how it looks like. Yeah. So it has something that is not 0 for negative values of n. This is the impulse response. This means that this system, in fact, predicts what the output will be before you put the input. In fact, try it. Convolve this with x with anything, any signal. Let's say x of n. You see that you'll have y h of. I'm sorry. You see that you'll have y of n being an advanced version of x. Meaning, before you put the input x, the output knows that you have put the input and it produces an output. So this is basically causality. Time invariance. If you shift it in time, left or right, does it affect or not? Stability, same principle, yeah? And so on. And I just wrote an example there. I wasn't sure whether I will talk about it or not. But anyway, I think I'll not talk about it. But maybe I'll hint to this once I add something about this topic in there. Maybe I'll either copy the example in there, or I will refer you to this example, because I thought that it's an example that will give you exactly the same feeling of finding the properties and different properties of a system, but now in discrete time rather than in continuous time. Okay. Now I'll talk about the topic that you have not seen before. Okay, and then we'll go to the last topic, which is called the Z transform. And the Z transform, by the way, is in my opinion easier than the transforms. Right? Let's talk about something called finite and infinite impulse response systems. Okay? Those are always abbreviated finite impulse response, FIR. Okay? And the infinite impulse response is abbreviated infinite impulse response. Okay? I'll just give. I'll not go into detail. This is, in fact, a topic that requires. Whenever you talk about what they call FIR or IIR filters, designing those filters you can spend courses and courses on just learning the basic concepts of finite impulse response and infinite impulse response filters. Okay, but let me just give you a hint of what is the difference between those and what do they mean. Sometimes, if you have, let me give you the following example, and I hope that you'll understand the theory. Let's say the idea of FIR and IIR systems or filters, let's say, or whatever. Right? If I have a room, like for example, I'm in building 68 now, and if you go up in the lectures, you see when I talked about the impulse response of systems, I put 2 or 3 figures in which I try to find the impulse response for audio signals, one at my home in in the living room in my home, it's kind of an open area. Yani the two floors, the upper floor and the lower floor, are open on each other. Just about few meters. Yani it's not the whole. My house is not big, okay, but part of the lower floor is open on the upper floor. I sat there. I brought my computer, sat there, and clapped. You remember when we were talking about the impulse response? I clapped and recorded the echoes, let's say, of my clap in there. And I found that I think it extended for about 0.8 of a second or 0.7 of a second or something like this. Right? Now, in theory, if you think about it, the impulse response there should extend from 0 all the way to infinity. Why? When I clapped, what happened to the sound that came from my clap? Part of it went immediately to the computer, right? Without hitting any objects. And my computer registered this. It probably was the closest, or it was, let's say, the strongest signal. So it registered something in the microphone or on the program that I was using that was very high. But what also happened, that clap that I did hit the wall that was near me. I think it also hit the floor. And it came back to the same computer after maybe 1/100th of a second, for example. And that echo caused another signal to appear in the impulse response. Not only that, now also the signal that came from the floor went and hit the ceiling and came back. And it registered another signal there, probably smaller in magnitude, but it registered something there. And then that same signal also hit the ground and came back, and so on. And this process continued. Theoretically, it will continue forever. Why? Because echoes, when you produce a sound, the echoes keep hitting walls and so on. They don't say, well, we have hit the walls 10 times, so now we have to stop. It's just that after a while, after maybe hitting 10 times or 15 times or 20 times or 100 times, the amount of power that gets reflected becomes weaker and weaker and weaker and so on, to the point that your microphone will have difficulty in hearing them. So you assume that after, for example, 5 seconds, this becomes equal to 0. But in practice, if you have a very strong microphone and a very good quality signal, let's say, system, you probably can find those echoes for the next 2 hours, maybe. Maybe 2 hours is an extreme, but at least you'll be able to find those echoes very small, but they will continue like that. If a system has an impulse response that looks like this, that extends to infinity, we call it infinite impulse response system. Because even putting a simple signal like an impulse into the system, when does the effect of that impulse disappear? Never. Until infinity. Its signal always remains there. Or let's say its contribution to the output continues there until theoretically infinity. Okay? This is what we call infinite impulse response filters. Okay? Now, there are some systems in which, for example, an idea came to my mind, but I'm not going to say it. I think it's inappropriate. Okay, if you have, for example, let me see. I'm trying to think of a situation in which we have a finite impulse response, something that you will understand. Okay, if I take, for example, clay. I think clay, العجين or طين or something like this. Okay, and throw it on the floor. What happens to it? It sticks. صح? It does not bounce. Think of the sticking there as if you have throwing something on the floor. Okay, is like an impulse, and it's just a single impulse, meaning the output of that system, or let's say the impulse response of that system, is only a single impulse. However, in fact, maybe this is another example for infinite impulse response. If you have a ball that is very elastic and you throw it on a concrete wall, or I'm sorry, not a concrete wall, but let's say on the floor, where the floor is made out of marble or some very stiff material, what happens to that ball? It keeps bouncing and bouncing and bouncing. This is exactly like an infinite impulse response situation. But if I have something that is not very, very elastic, like, for example, clay or something like, maybe even a rubber ball, it will hit the floor 5 times and then it will stop. So this is like a finite impulse response system, meaning that any input that comes to the system will produce an output in the next 5 or 10 or 15 samples only. And then no outputs will happen after that. And due to that input that you have put, the output will stop due to the input after maybe 10 seconds, or not 10 seconds, 10 samples, or 20 samples or so. This is basically the difference between finite impulse response and infinite impulse response. I'll just summarize it very quickly. Finite impulse response, gentlemen, okay, means that an input will produce an output for a finite number of samples. The finite number could be 5, could be 10, could be 1,000,000, but it's finite, it's not infinite. Infinite impulse response filters, gentlemen, or systems, are systems that once you excite them, once you give them a single input, that input will keep repeating, let's say, or will keep affecting the output forever. Finite impulse response, now, this is basically the meaning of those two. If you look at the block diagrams of finite impulse response and infinite impulse response, how do they differ? Finite impulse response, FIR, and infinite impulse response, okay? Finite impulse response do not have feedback, typically. For example, you might see something like this. Delay. Delay. For example, something that looks like this. Plus, plus, minus. And maybe even another one in here where I have multiplied by 5. Something like this, okay? If you put it in there also. Okay? This is a finite impulse response filter. Why? The input x of t that, or x of n that you put will do something in here and then will appear at the output. This also will maybe be delayed, and then after that will appear at the output. And maybe be multiplied by something and will appear at the output. But after maybe 1, 2, 3 seconds or so, خلاص. If this input becomes equal to 0, the 0 basically will propagate to the output and you'll get nothing. And meaning, any impulse that you put at the input will only have an effect for 3 or 4 seconds, or two. In this situation, it will only have an effect for 3 seconds. At the time you put the input, at 1 second, at the time you put the input, it will appear through this path. Because this path does not have any delay. The lower path does not have any delay. It just multiplies the input by 5. It will also happen, or it will also have an effect because of this delay. So after 1 second, also part of this input that you put will appear at the output. And after 2 seconds, because in here, assume that I have 2 delays there. Right? After 2 seconds, also this input will propagate in here and it will appear at the output. But after 3 seconds, خلاص, everything is gone. But nevertheless, this is what we call a finite impulse response filter. Infinite impulse response filters will always have feedback. Something that looks like the integrator, for example, that I've shown you. Okay? Maybe a delay, and then you're adding in here, something like this. Okay? If you have feedback that takes something from the output and feed it back to the input, this means anything that you put in here will appear at the output, and then this same thing will affect the input, or let's say it will appear as an input that will affect the next output, and it will affect the input that will affect the next output, and so on. And this effect will continue theoretically forever. Those are called infinite impulse response filters or systems. Okay, Juan? Right. Okay, I think I have only 5 minutes. Now let me talk about the Z transform. Do you have any questions, gentlemen? Any questions? Right. The Z transform is quite simple, gentlemen. What I will do is I'll start discussing it, okay? And we'll continue next class. And you'll see that in most situations, it's much easier than the other two transforms, the Fourier transform and the Laplace transform. In fact, some of the ideas of the Laplace transform, we'll use them there, which is the partial fraction decomposition, okay? But anyway, let's say that this is basically the definition of the Z transform. Okay? The Z transform of a signal, time domain signal, a discrete time signal, okay, is equal to not the integration, but the sum from, by the way, again, for the Z transform, we have the bilateral Z transform and the unilateral Z transform. We're only interested in the unilateral, which means that we're integrating from 0 to infinity. The bilateral, I'm not integrating, but summing. Okay? The bilateral, you have the sum from minus infinity to infinity. We will not talk about this. Forget about it. Okay? So we are only interested in the unilateral Z transform, which means we are summing from 0 all the way to infinity of the time domain signal x of n, discrete time signal x of n, multiplied by z raised to the power of minus n. What is z? Z again is a complex frequency. Just like S in the Laplace transform, Z is nothing but a complex frequency. Okay, fine? This is all I want you to know about the Laplace transform. Now, the good thing about the not Laplace, I'm sorry, the Z transform. The good thing about the Z transform, because it applies on discrete time signals, I can always expand the Z transform as a series. If you think about it in here, if I plug in different values of n, this probably will be the last thing that I mentioned. If I plug in different values of n equal to 0 in here, and n equal to 0 there, and then n equal to 1 and 1, 2 and 2 and so on, you see that the Z transform of a signal, I'm assuming, by the way, that the signal is 0 or not 0 only for values of x that are greater than 0, greater than or equal to 0, meaning x will look something like this, 0, 0, 0, 0. And in here, it could be something in there. Okay? So in here, it's all 0. Okay? Then, even if it's not 0, the unilateral Z transform will take care of it. It's only adding, or let's say it's only considering the values of the signal that are to the right, let's say at 0 and to the right of the y-axis. It's ignoring the values that are to the left of the y-axis. So if you expand this, you see that it's equal to x of 0 plus x of 1 multiplied by z inverse, or z to the power minus 1, plus x2 multiplied by z inverse raised to the power of 2, and so on. Okay? Now, you remember when I talked, this is the last thing I promised you that I said. You remember when I talked about that delay box, I put a d there, and I said that some people will remove the d and write z inverse. Do you know what z inverse means? It basically means a delay. Look, this is the sample of the signal. Yeah, the Z transform combines or collects all of the information of the signal in the following form. It says that the Z transform of the signal x is basically the sample which exists at 0 plus the sample that is at 1, the value of the sample at 1, but it's delayed by 1 sample period from it, plus the sample that comes at 2, the value of this sample, which is 2 or 5 or minus 3, but that value is not added to the 0 or added to the 1. No, it is delayed then the sample that is here by 1 second or by 1 sample, and delayed compared to this sample by 2 seconds. So in fact, if you think about it, Z inverse, or Z to the power of minus 1, indicates that that sample that I have, what time it comes at. If I have Z to the power of minus 1, it comes at t equal to 1, or at n equal to 1. If it's multiplied, if that sample is multiplied by Z to the power of minus 7, this means that it comes at n equal to 7, and so on. This is how you can combine all of the information of the signal in a single line without the different values of this signal combining right away. And if I didn't put the Z's, this, if I just added those X's, I'll get X0 plus X1 plus, okay, which will be a number. Now, clearly, by doing this, you have combined all of the information into a single number, which means that you have lost the data. But by multiplying each one of those by a Z raised to some power, this indicates where does that sample come at. Okay, so I'll stop at this point in here, and inshallah, next class we'll talk about the Laplace transform, the Laplace transform properties very quickly. They're simple, okay? And then the inverse Laplace transform, and this will conclude our course. Okay, Juan? فخلاص, inshallah, I'll meet you tomorrow. Unless you have any question or so, please ask. If you don't have any questions or so, inshallah, I'll see you tomorrow.
Doctor, you said the Laplace transform. Do you mean the Z transform?
لا يعني in my discussion here it was about the Z transform, but I mentioned a few minutes ago the Laplace transform because if you remember the partial fraction decomposition in the Laplace transform, we will also use it in the same principle in here. But يعني clearly my discussion here was about the Z transform. My apologies if I said the Laplace transform. This is, by the way, this is maybe a problem with me. When I get involved with something for a while, it becomes very difficult for me to forget it and go to something else. So over the past several weeks, I've been working with the Laplace transform, creating for you the notes and the lectures and so on. So I'm still in the mentality of the Laplace transform. Okay, but yeah, but certainly I meant the Z transform. My apologies for this.
Okay, thank you, Doctor.
Sure. Now,
Doctor,
any other question? Totally. Yes.
Doctor, I see the delaying is kind of time shifting. What's the difference
Yes.
between them?
It is. The delay there, you see, the difference between time shifts in continuous time is that the time shift can be any value. It could be 1, it could be 2, it could be negative, it could be fraction, it could be 1/2. Okay. The Z to the power of -1 indicates a delay by one sample. This is why I do not have Z to the power of 1/2. Because Z to the power of 1/2 indicates a delay by 1/2 of a sample. And we said that we are not allowed to have a delay of 1/2 of a sample. Okay. بيني وبينك الآن, okay, Z to the power of -1 doesn't exist. But if you decide to go into the field of digital signal processing, you might learn that there are some Z to the power of -1. Yeah, there are some. Yeah, you could think of Z to the power of -1/2, okay, which is called fractional delay. But at least in your course, forget about this. Always, whenever I say Z to the power of -1, immediately it should come to your mind that we are talking about a delay by one sample. Meaning, if I tell you, okay, let me tell you this. Assume that I found the Z transform of two signals, capital X of Z and capital Y of Z. This is equal to 3 plus 2 Z to the power of -2 plus 5 Z to the power of -3. Okay, and the second one is 3, 2, and 5. Same numbers, but this is Z to the power of -1, and this is Z to the power of -3. Do you think that the signals X of n and Y of n are the same or not? You see, both of them contain 3, both of them contain 2, and both of them contain 5. Are they the same?
I think they're not, because
Why not?
the delay in the first one is Z of -2.
You're right. Yes. معناه, look, both of them occupy the samples from 0 to 3. From 0 to 3, and 4 samples. Okay? But each one of them has one of the samples equal to 0. The 3 basically represents, if you sketch them, and if you sketch X of n, the 3 basically, since it's not multiplying by any Z, it basically comes in here. This is 3 at 0. 1, 2, and 3. Okay, this is X of n. This is the first one. Yeah, the 3 basically is the sample that exists at n equal to 0. The 2 there is the value of the sample that comes after 2 seconds later. So not at 1, but at 2. This is 3, and this is 2. Okay, and the 5 is the sample that comes 3 seconds later, or 3 samples later. I'm sorry. If I say seconds, I meant samples. So the 5 is the sample that comes, or the value of the sample that comes 3 samples later. Okay? So it is here. This is in fact X of n. If you come to Y of n, it will have the same value in here. But this value that I have there will come in here. Okay? And the same value that I have in there. Okay? How did I get this? It's by looking at what are the values of Z, or what powers of Z I'm multiplying each one of those samples by. So basically those indicate to me where are the locations of the samples. This is basically why the Z transform is quite simple. In many situations, you can almost get the Z transform of a signal just by looking at it. Just multiply the different values in there of the samples by this one. You multiply it by Z to the power of 0. Multiply this one by Z to the power of -1. Multiply this by Z to the power of -2. Multiply this by Z to the power of -3. And that's it. I am assuming that the other samples are 0. Okay, so I don't know if I explained it to you well or not, but this is basically how you can deal with.
Yes, it's clear, Doctor.
طبعا it's the situation is slightly more complicated, and I'm just trying to simplify it for you, and maybe I have oversimplified it. But inshallah, next class you see what happens when we try to find the Z transform of different signals, okay, and then the inverse Z transform, okay.
Okay, thank you.
Okay. Any other questions, gentlemen?